In this video, we will consider the interference effects from thin films. Right? But before we even start, we need to address what happens when light is reflected at an interface. Right? Let's see if you can guess the answer. Imagine that we redo Young's experiment, but instead of having two sources, we use a mirror. Right? Then what happens to the interference pattern on the screen? If you look at the path difference between the two rays, the blue one and the orange one, it is the same as in Young's experiment. The light travels the same distance from the source S to the mirror as it was traveling from the second source in the original Young's experiment. So if the path difference is the same, then you would expect the interference pattern to be the same. And it turns out that the position of the fringes are reversed in this case. So when in Young's experiment there was a bright fringe, then with the mirror we have a dark fringe. And when there was a dark fringe in Young's experiment, now we have a bright fringe. And the reflection on a mirror, in fact, introduces an additional phase shift of pi. And so the electric field is shifted exactly so that a maximum is now corresponding to a minimum and vice versa. And so something you will learn later in physics classes is that the reflected electric field depends on the index of refraction of the two materials at the interface. The index of refraction is the ratio of the speed of light in vacuum by the speed of light in a material. So if you have two materials in which the speed of light is different, then they will have different indices of refraction. And so, for example, NA will be the index for one material and NB will be the index for another material. And if an electromagnetic wave is incident perpendicular to the interface, then there will be a reflected wave. There will also be a transmitted wave inside the second material, but here we only care about the reflection. So only care about the reflected wave. And the amplitude of the electric field that is reflected will be given by NA minus NB over NA plus NB times the incident electric field. And you can see that if NA is smaller than NB, that means if the light travels faster in material A than in material B, then the reflected electric field will have the opposite sign as the incident electric field. And since minus cosine omega t is equal to plus cosine omega t plus pi, then instead of reversing the signs, we can simply add a phase shift of pi. Right? So if NA is larger than NB, that means if the light travels slower in material A than in material B, then the reflected electric field will have the same sign as the incident electric field. And there is no phase shift in this case. In fact, this is not really new. We have already seen that for a wave on string reflected by a fixed end, the wave pulse is reversed. And we have seen that a positive pulse comes back negative and a negative pulse comes back positive. We have also seen the same effect for torsion waves and also for sound waves. And now you know it is the same for light. Right? There is an analogy with strings, for example. Remember that the wave speed on a string is given by the square root of T over mu, where T is the tension of the string in Newton, and mu is the mass per unit length of the string in kilogram per meters. Right? So for a thick string with a large mu, the wave speed will be slow, which corresponds to a large index of refraction. And for a thin string with a small mu, the wave speed will be large, and this corresponds to a small index of refraction. So the index of refraction is like the thickness of the string, large N, thick string, small n, thin string. And now, if you look at the reflection of a wave pulse, when we go from a fast to slow wave speed, you can see a phase shift of pi. And when you go from a slow to a fast wave speed, then there is no phase shift. Now let's see if we can see that on the torsion wave. I coupled two torsion waves, and first I am going to do the case from fast to slow. Okay, this was very quick, so let's see it again in slow motion. You can see the incident wave with a positive displacement, and focus on the reflected wave here. You can see that the reflected wave has a negative displacement. So for the reflection from fast to slow, there is a phase shift. Now let's look at the other case, from slow to fast. Again, the slow motion is convenient. Then you see that the reflected wave remains with a positive displacement. And so there is no phase shift for the reflection from slow to fast. One more thing, we have to cover that there is a change of wavelengths in a material. We've just introduced the index of refraction as the ratio of the speed of light in vacuum to the speed of light in a material. The fact that the speed of light is different also means that the wavelength is different. And you can see that if you remember that the wave speed is equal to lambda over t. So in vacuum, we will have c equal lambda 0 over t, where lambda 0 is the wavelength in vacuum and t is the period. And in a material, then the speed of light is v equal lambda over t. The period remains the same because the frequency remains the same, but the wavelength is modified. And in fact, in a material, the wavelength is smaller because the speed of light is smaller. And the wavelengths are related by the relation that n is equal to lambda naught over lambda. Now, we've pretty much covered the two main concepts for interference in thin films, right? So remember, there is a phase shift for the reflected wave at the interface from a fast to a slow medium, and the wavelength in a material is smaller compared to vacuum. Right? The rest of this video has nothing new, so instead of continuing a lecture, I will cover an example of problem. Right? So in this example, we consider an air wedge. Right? This is like a thin film of air that has a variable thickness. It can be created by two pieces of glass with a small angle between them, and the light can be reflected from the top of the air wedge or from the bottom. And the two reflections will interfere with each other. And because the thickness increases, it will produce a set of bright and dark fringes when looking at it from the top. The two example questions that we will try to answer are what is the spacing of the interference fringes? And what is the fringe at the line of contact? Is it bright or is it dark? To answer these kinds of questions, your strategy is to find out the phase difference between the two reflected rays. Right? So first, the path difference is 2t, where t is the thickness of the layer of air. Right? We consider normal incidence here, so we neglect the small angle on the figure. Right? The angles are exaggerated so that you can see the two rays of light, but in reality, they are vertical on top of each other. Right? Next, we should address if there is an additional phase shift due to the reflection or if there isn't. Right? So first, for the reflection at point A, we have an interface between glass and air, so between slow to fast. So there is no phase shift. Second, at point B, we have an interface between air and glass, so from fast to slow. And so in this case, there is a phase shift of pi. Then we need to consider the wavelengths, right? The path difference of 2t happens in air, so the wavelength is the wavelength in air. So in this case, the wavelength is not modified. Now we are ready to calculate the phase difference, right? So remember, the phase difference is k delta r plus any phase shift. So we have k delta r plus pi, because we have phase shift of pi at point B. And since k is 2 pi over lambda, and since delta r is 2t, we can write that the phase shift is, the phase difference is 2 pi over lambda times 2t plus pi. Now, we can write the condition for constructive or destructive interference. If the phase difference is equal to m2 pi, then we have constructive interference. And if the phase difference is m plus 1/2 2 pi, then we have destructive interference. And you can rewrite these equations. The first one gives you that if 2t is equal to m plus 1/2 lambda, then we have constructive interference. And the second one gives you that if 2t is m lambda, then we have destructive interference. So you can see that as the thickness is changing, we will have a succession of constructive and destructive interference. Now, to get the spacing, we need to introduce the variable x in these equations. And we can introduce the angle alpha so that we have tangent alpha is equal to t over x. And it is also equal to h over L. And so x is equal to TL over h. Then I can reuse the relations for t, and I obtain that if x is equal to m plus 1/2 lambda L over 2h, then I will have a bright fringe. And if x is equal to m lambda L over 2h, then I will see a dark fringe. So we can answer the first question. The spacing between the interference fringes is delta x is equal to lambda L over 2h. And we can also answer the second question, because if you look at x equals 0, then that corresponds to m equals 0 for a dark fringe. So the fringe at the line of contact is dark. So remember the technique to solve that kind of questions. First, find the phase difference. For this, you will need to know two concepts, right? What is the phase shift at the reflection points, and what is the wavelength in the material? And then write the interference conditions. If the phase shift is m2 pi, then we have constructive interference. And if the phase difference is m plus 1/2 2 pi, then we have destructive interference, right? And the rest is just mathematics. Right? So to make sure you understood, let's do it again, right? This time we replace the material inside the air wedge by water. So it's a water wedge, if you want. So this time the path difference is still 2t, right? This has not changed. At point A, we have an interface between glass and water. So the index of refraction of glass is 1.6, and the one for water is 1.33. So the interface is from slow to fast, and so there is no phase shift. Then at point B, the interface is from water to glass, so from fast to slow. So there is, again, there is a phase shift of pi. This time, the path difference of 2t happens in water. So the wavelength will be shorter, and it will be lambda 0 over n water. Then we can calculate the phase difference. It is the same as before, but instead of 2 pi over lambda, we now have n water 2 pi over lambda 0, right? Because the wavelength in water is different. And then we can write the conditions of for interference. When the path difference is m2 pi, we have constructive interference. And when the phase difference is m plus 1/2 2 pi, then we have destructive interference. And we can rewrite this in terms of thickness. We obtain the same relations as before, except that lambda is replaced by lambda 0 over n water. The rest is all the same mathematics as before. But we have to replace lambda by lambda 0 over n water. You see that the spacing of interference fringes becomes lambda L over n over 2 n water h. Right? So because the wavelength in water is reduced, the spacing between the interference fringes is also reduced. Now, usually the number one request from students is to get more examples of problem solving. So let's do it one more time. so that you really memorize the strategy, right? But this time, let's replace the water by grease and the top plate by plastic. Right? The bottom plate is still glass with a refraction index of 1.6. Then we have grease with a refraction index of 1.5 and plastic with a refraction index of 1.4. And we have the same questions as before, so we will use the same strategy, but because this is the third time, then we will do it faster. So first, the path difference is 2t. This is still the same. Then at point A, we have an interface between plastic and grease, so from fast to slow. So there will be a phase shift of pi, and the rest after that will be the same as before, right? Then at point B, and you see that we don't have an additional phase shift here because both rays have the same phase shift of pi, so there is no additional phase difference between them. We can continue the rest as before. So we can answer the first question. The spacing of interference fringes is given by delta x is equal to lambda 0 L over 2 n grease h. Again, you see the spacing between fringes is reduced because the wavelength is reduced in grease. And we can answer the second question. You see that the fringe at x equals 0 will be obtained for m equals 0 for a bright fringe. So the fringe at the line of contact is going to be bright. Right? This is different from the previous example, and this is because of the difference in phase shift at point A. All right, so I hope that with these examples, you will be able to solve any problems with thin films interference. One question that you may be asking yourself is, why do we only consider the light reflected at point A and point B? Why we don't consider the ray of light at point C or at point D? Right? This is definitely a good question, because there is definitely some light that is reflected at those points, right? So why do we ignore them for the interference? And in fact, this is something we mentioned in the first video on physical optics. It has to do with the thickness of the film. If the film is thinner than the coherence length of the photons, then we can consider the two reflected waves to be coherent with each other. But if the film is thicker than the coherence length of photons, then the two reflected waves are not coherent with each other. So they don't have a constant phase relationship between them. So we would not see a constant and stable interference pattern from them. Since the plates of glass are usually thick, only the air wedge in between can be made thin enough to produce an interference pattern. Of course, keep in mind that the angle is really exaggerated on the schematic. In reality, the two plates are almost touching each other and the air wedge is very, very thin. There are several examples of applications. One example is called Newton's rings. It is the same situation as in our example, but instead of an air wedge produced in between two plates, we have a lens. And so in the case of a lens, then the fringes are not equally spaced because the thickness is not linear. And because the lens is circular, we see circular fringes. Right? They are called Newton rings. And each time the path difference is equal to one more wavelength, then there will be one more ring. And since the path difference is 2t, then each fringe indicates an additional half wavelength, lambda over 2, between the two lenses. And this is very precise, right? Remember that for visible light, lambda is about around 400 to 700 nanometers. So being able to see a change of thickness of a few hundreds of nanometers is really impressive. And this is used to test the quality of lenses with high precision. Right? You put a master lens for which you know the curvature, And on top of the master lens, you put a lens that is being tested. And if there is a small gap between them, half of a wavelength, then we start to see Newton rings. And because this depends on the wavelength, you can, if you use natural light instead of a laser, then you can see colors because the interference condition depends on the wavelength, right? So each different colors will interfere constructively at different positions. Another example where you see colors is when you have a thin layer of oil on the surface of water, and this can happen when there is a major oil spill or even a smaller spill, right? Unfortunately, we can often see that kind of interference colors from near boats, and it makes me sad, really. Sometimes you can also see those thin film interference colors on soap bubbles, and this is a little more clean. Right? As you probably know, a soap bubble is a thin layer of water in between two layers of soap. And water is moving in this layer, and the thickness varies, which produce those moving colors that you can see on bubbles. Right? Eventually, the water drains out, and the thickness becomes very too thin, and then the bubble pops. There are also colors in nature that are coming from interference effects. Right? For example, the blue color of a certain butterfly is not the result of pigments, but the result of interference between the reflections on multiple flanges. The spacing of the flanges is so that constructive interference happens for the blue wavelengths, and so the butterfly appears blue. Another example, if you fish or if you buy fish at the market, you may have seen that you have shiny reflections of light on the fish scale. This is also an interference effect due to several layers with a thickness that is in the range of hundreds of nanometers. And the color that is most strongly reflected from a platelet will depend on the angle at which it is viewed. And there are a lot more examples. In fact, if you're interested about more examples, you can check out the Wikipedia article on structural coloration, and you will find a lot more examples of interference in nature. An example of application is the anti-glare coating on glasses. So there is a thin films of a material with a refraction index that is intermediate between the index of glass and the index of air. And a typical coating is magnesium difluoride, for example. And if the thickness of the film is lambda over 4, then the path difference is lambda over 2. So the wave is shifted by half a wavelength and produce destructive interference. And so that means that there is no reflection because the reflected light interferes destructively. One problem that is that we have with those coatings is that it only works for one wavelength, right? So usually the thickness is chosen to remove the glare in the yellow-green because this is where our eyes are the most sensitive. And so that means that there is some reflection for the red and the blue wavelengths. Now, the light that is not reflected then is transmitted. And sometimes this is something that you want. For example, if you're designing solar panels. The solar panel is designed to avoid to reflect the yellow so that the sunlight, most of the sunlight is absorbed. So the solar panel does not reflect yellow, and that's why it appears blue. The best solar panels, they absorb more wavelengths, and so they appear even more black.